Hey everyone, my name is Shahir, and I am the VP of Educational Technology at the University of Toronto Design League. Today, I will be presenting the second workshop of our ANSYS series, which will be on ANSYS simulations using the program ANSYS Workbench. The purpose of this workshop is to get you familiarized with the foundation of simulations and help you get started on the ANSYS Workbench software so that you can start performing your own simulations for your engineering design projects. Before I go any further, I would like to speak a bit about UTDL and sort of the things that we have to offer this year. So this reading week, actually, we will be having a joint event, a joint mini competition event with the Applied Architectural and Landscape Design Club from the Daniels faculty at U of T. It's a joint collaboration where teams will be paired up with engineering or architecture students to help design their own dream transit system or dream transit design that can help improve foot traffic around campus or in between certain buildings. Feel free to check out our Facebook or Instagram pages for more details on that, and please do sign up if you're interested. It's going to be a really cool event, and you'll be able to interact with architecture students to work on a design problem. And you'll be able to, if applicable, depending on your design, you can apply the things you learn from this workshop to your project. We also have our 3D printing workshop coming in the week after reading week. So watch out for any announcements regarding that. And next semester on February, we will have our annual designathon, where there will be lots of great prizes to be given out. So follow our Instagram, like our Facebook to be up to date on that. So let's, without further ado, let's get started. If you want to follow along, feel free to open up ANSYS on your own personal laptop or log into ECF and open up Workbench through there. We'll be going over through the basics of the program, so you can, to get more familiarized with the program, you can follow along like that. So for the agenda for this workshop, and sorry, one more thing before I go in are 3 key things that I want to share with you all. Just gonna post them in the chat real quick. So if you don't have ANSYS on your computer, you can go ahead and follow the link in the chat to download ANSYS on your personal laptop like so. It's completely free, and you'll be given a 1-year license, which you'll have to renew once a year. For this workshop, there's going to be an aid sheet that you can follow along, that you can take home with you for reference while you're working on your own projects and whatnot. It's a very useful guide to just brush yourself up on some key concepts that you might forget. And lastly, for this workshop, just like all other workshops, we are hosting a raffle. Sorry, one second. We are hosting a raffle for a $25 Amazon gift card. So if you are interested in winning the raffle, then the link is also being posted in the chat right now. Yes, it says Space Clean, but it is for ANSYS simulations. All right, now with that out of the way, we can go ahead and get started with the workshop. So the agenda for today is I'll first be just reviewing the motivations behind simulations, why it is important in design projects, and why you should be implementing it in your design projects today. I sound like a marketing person, but it's true. Then I'll be going into the basics of Workbench. I'll be opening up the program and going through the basic interface so that you don't feel overwhelmed when you first open the program. I'll be going over 3 analysis modules that you can perform on Workbench. One will be static structural. Next will be steady state thermal. And the last one will be explicit dynamics. And lastly, we'll wrap it up. We'll be going a bit more in depth in a static structural example. In this example, we'll be going over the types of questions you should be asking when performing a simulation so that your results make sense and that they can be applicable to your real life prototype or project. And then lastly, I'll be taking any questions if you have any, and that will be it for the workshop. So last week, I spoke about the engineering design process that you might be familiar with in your first year engineering course. In the middle, you have your project space, which is the space where you and your team will spend the majority of your time thinking about the project, creating solutions, testing them, and getting your final result before you present it to the client. I'm going to argue, for argument's sake, that the testing phase can be one of the longest phases in this process if you adopt traditional practices. Now, what do I mean by traditional practices? I'm going to go back to what I was talking about last week, is say if you had to design a sort of carrying device to carry your gardening tools from point A to point B in your garden. And this is like, in the Stone Ages when the wheelbarrow hasn't been invented, then your team, without any CAD software, CAD tools, might design the first generation wheelbarrow, but then realize that the support that you made can't even support the wheelbarrow's own weight. And a more effective, more efficient step than just diving into your first prototype would be to open up a CAD program and design your model, your initial model, on a CAD program and simulate it for any peak stresses or for any failure modes that might occur. And so that you can iterate within that design space until you have a final design, which you can bring out for testing. And then your testing phase will be a lot more smoother. Using CAD design, you can study things like heat transfer, impact analysis, and fluid dynamics, and overall will help you increase your productivity, improve the quality of your design, save you a lot of time, save you a lot of money because you won't have to go and procure materials for a million prototypes, simplify sharing between teammates, and saves your sanity. But there's an asterisk on saving your sanity, in the sense that it will only save your sanity if you are familiar with using the CAD program, which is why it is important to learn about CADing and simulation before you actually dive into doing it, or else you'll be pulling out even more hairs than you might have thought. So this is an old slide, but the steps are relatively the same. If you want to download ANSYS for yourself, you can go to the link above. It's also in the chat. And you can go and click on ANSYS Student, check your system and browser requirements, and then go ahead and click download. It's about 6 gigs or 7 gigs to download, so it'll take a while. And once you have it downloaded and installed, you can type in Workbench in your search bar to open it up on your laptop or computer. So now I'm going to be going into ANSYS Workbench, showing the basics of it, and I'll be diving into simulations and the steps to perform a simulation thereafter. I'll just stop sharing for a second. All right. Hopefully you guys can see the right screen. If you can't, then please let me know in the chat. But this is what your Workbench screen would look like with the exception of these modules right here. So typically, when you open up a fresh Workbench file, you would have a blank project schematic with things that you would want to put in. Now, what would you put in to the schematic? Well, you would be putting in analysis modules. For example, right here, this C box right here is one analysis module. And as you can see, they all contain different analysis modules contain a similar amount of steps. And that is, as we go down the list, it is first you see if I can, no, that's the most I can zoom in. You can first select your materials for your model. Then you actually model it, or you can import your model if you already have it pre-made. This is using the SpaceClaim software that we went over last week. And then last, it will be modeling and simulating your design to get the results that you need. Steps 4, 5, 6, 7 are all encompassed in this analysis section right here. So in general, there are only 3 steps. There's engineering data, geometry, and model. I'll be going over each of them in more detail in a second. So how do you input a model in the first place? What you would do is you would go to the left-hand side where you see toolbox and look through the analysis systems down here. Say if you want to perform a static structural simulation, all you have to do is click and drag your static structural. And as you can see, these green boxes show up, showing me places where I can create a standalone system. Could really be anywhere, but if I place it and just drop it right here, you can see the static structural has been made. Now, say you're working with multiple studies, whether it be you're working with static structural and explicit dynamics, or you're working with 2 static structural studies, but with 2 different geometries, 2 different models. Then what you could do is you can bring in multiple, let's say if I bring in an explicit dynamics analysis module right here, I can link my data between these modules so that it can save me a bit of time so that I don't have to re-enter or recreate my geometry or my data. So for example, if I know I'll be using the exact same materials from engineering data for my static structural study, I can just click and drag so that they become linked. So that my engineering data over here becomes linked with my engineering data in explicit dynamics, so that I'll be able to select the exact same materials. This is especially important when you're creating your own materials and you don't want to have to re-input the material properties every time you create a new study. This linking of data can also be done for geometry, and it can also be done for modeling, but I wouldn't recommend it because your results you may have to like readjust a lot of things for that anyways. So ignoring these 2 modules, E and F, I initially had, let's see, get rid of these 2. Yeah. So I have the 3 modules that I wanted to go over today, and that is static structural, explicit dynamics, and steady state thermal. And down here will be our example. So let's go through static structural and how we can actually perform a static structural simulation from the bottom up. So we start with engineering data, and to start, all you have to do is double click on engineering data twice, and you can see a new tab has been opened within Workbench. Now, all of this might be a lot for you, so I'll be going over each box individually so that it will be a bit more digestible. The first box that you should look at is the middle box right here, the outline of schematic. Here is where you can find your library of materials, as well as when you click into a library, the list of specific materials. So so by default, you'll be given a couple default options like a structural steel or aluminum alloy. To add more materials, what you would have to do is you'd have to go to this top left corner right here and click on engineering data sources. Once you click on that, you can see that you'll be greeted with a list of libraries that you can choose from. Depending on the study that you'll be doing, the material will be relatively important. So for example, if you're just looking to do a comparative study between wood and iron or steel, then you might go for just general materials or granted materials for simulation. If you're, say, doing a study where you're looking to observe the failure of a specific material, then you would probably have to go to either explicit materials or non-linear materials, because those materials would have material properties or material data in the plasticity region of that material so that you can actually see it in your simulation. So if you want to add a new material, all you have to do, so far I have air, structural steel, and liquid. All you have to do is just double click into a library. Say if I go to into the granted library, you can see that there's a huge list of materials that I can choose from here. And if I want, say, structural steel, I can just click this plus button to add to my personal library. Now, when you click on, say, a specific material in the library, this bottom box right here will list its material properties, any that are included within this one right here. So as you can see, we have the density with its units, tensile strength, ultimate tensile strength. And as you can see, some don't give a value, some just give a symbol tabular. That means their data is tabulated, and you can see their data in the top right corner over here. And any tabulated data will also be shown as a graph in the bottom right corner right here. So really the only two tabs, the two boxes you should be looking at are that you need to be looking at is your libraries tab and your material properties sort of tab. And if necessary, you need to look at tabulated data. So now let's say you've looked through your engineering, your libraries of materials, and you can't really find the exact material that you're looking for. It doesn't have the exact properties that you want. Well, you can add your own materials using the following steps. So what you can do is you can just click off of engineering data sources to bring it back to your personal library. And you can just click right here to add your new material. It could be whatever you want. Let's say if I want to call it blue, I don't know. I'll call it blue. And as you can see, I have a new material made called blue. But as you can see, there's no material properties listed. To add material properties, what I would do is I would go to the toolbox section right here, and whatever material properties that I would want to add, I would just click, drag, and drop, or double click. And then it would show up as a material property that I can enter in the highlighted section. So say if I want it to be 4,500 kilogram per meter cube, then I can do like that. Going back to blue, say if I want to add, let's say, linear elastic isotropic elasticity, double click that. And I could add in whatever I need to do for that. If I just expand this a bit, for isotropic elasticity, it'll ask me to enter in the Young's modulus or the Poisson's ratio. So depending on what material properties you want for your material, you can just double click and enter material properties as you need. Okay. So once you're done with getting your list of materials together that you'll be using for simulation, all you have to do is just click off engineering data, and that'll be it for selecting your material selecting your data or your materials. Next, you will be going into your geometry step, where you will either be importing or creating your new geometry in SpaceClaim. So if you had a fresh new module and you double click geometry, you would open up SpaceClaim with the fresh and with an empty file, and then you would just create your geometry within that file. In this module right here, I already have my specific design imported. And to do that, you'd be given an option to import geometry, and you'd just be given the option to browse, and then you can just double click and select your geometry like so. So let's go into the geometry, and let me show you what I'm trying to actually simulate in this workshop today. See if this hopefully it opens up. Let's share my entire screen in the meantime. All right, there we go. So this is what I'll be performing a static structural simulation today. Just in case I didn't clarify earlier, static structural means applying a static non-dynamic load to a material for, I guess, an indefinite amount of time. So just think of, I don't know, a 20-pound weight on your desk. That would be a static load on your desk. So in this example, we have a door. Now, let's say you wanted to get through this door, right? Common sense would tell you to, just turn the doorknob and open the door. But look at here, this doorknob is just a cylinder with a sphere attached. It's not an actual doorknob. Look at these hinges. These aren't actual hinges, right? Like, who made this, right? Like, this isn't a door. So this door is locked. You're trying to get you're trying to get through it. How do you get through it? The only other option that personally that I would think of would be to break it down, to kick it in. And let's say, you want to figure out how much force do I need to apply to break this door in? How much static force, how much static stress or pressure do I want to apply to this door so that it actually breaks open? So you would perform a simulation like that, being the engineer that you are. So, but then you go into simulation. Then what one thing you can do is, instead of simulating the entire door, all you really care about is the part of the door that you're trying to break. So you just model the sweet spot right here, and this spot right here is all we'll be needing to simulate. So to take a step back a bit into why I'm only modeling the sweet spot and not the entire door, is that sometimes your model can be very complicated, and it is easier for the computer to simulate small sections of your model rather than the entire model, especially if the vast majority of your model is not involved in the simulation itself. So, for example, when I'm kicking this door in with my foot, I don't care what happens to the hinges. I don't care what stresses happen on the hinges. I don't care if this top piece of the door deforms or not, right? All I really care is whether or not I achieve a peak stress on this sweet spot so that it breaks open or breaks apart from the rest of the door. And so that's all I'm going to be simulating. As you can see here, I've divided my door and my quote unquote sweet spot into two different solid bodies, and I've suppressed my door. Here it would be, say, it would have said suppressed for physics. I suppressed my door so that it does not show up in my simulation at all. And the only thing that will be showing up will be my sweet spot. This may be useful for you if you model your entire thing, but you only want to simulate one specific thing. You can split up from the rest of your model and then simulate that. Or I guess a better practice would have been to just model the exact thing that you're trying to simulate, just to make it a bit easier and time efficient. But I did it like this for the sake of examples and dramatic effects. So once you're done with your geometry, you can go ahead and just click off of Space Claim, and you can go into the modeling section where you can actually perform your simulation. So let me just double click that. Just a quick note, this is a common message that you might receive every time. Basically what this means is that every time you change your geometry or change your engineering data, your modeling software would have to just do a quick update to get up to speed to what you've done previously, so that it doesn't confuse itself. Just give it a minute to load up. In the meantime, I guess if you have any questions, feel free to drop them in the chat. If not, I'll be waiting for mechanical to open up. For a second, I thought mechanical wasn't opening up, but in the bottom left corner, it would tell me starting mechanicals. And now I know that, okay, it's trying really hard to open up mechanical right now. So give it some time. All right. So as you can see, when you open a mechanical, one good thing to note is that my material has made it in here in one piece. My door isn't anywhere to be seen. It's just my sweet spot, which is good. Now, just like how we went down a list on the analysis modules to complete a study, you would be doing the same thing over here, where you would be going down a list to make sure you have everything correctly made before you can actually perform the simulation. As you can see, most of this has already been done. So I'll be just going over the things that you should be adding in general. So the first step, as you can see, is geometry. And this step basically requires you to just check if your geometry has made it in one piece and to assign your material to your geometry. So the first step is to first check if there's your geometry came in one body, in which in our example it did. Sometimes you might have a model and it might come in two separate bodies, which could be an issue. So just be sure to watch out for that. Next, you want to assign your material. And to do that, all you have to do is to just click on it once, scroll down to details, and go to the material selection, material, and see assignment. And right now it says wood, which is, you know, what doors are typically made of. So that's the material I chose, oak wood. As you can see, it's a very general material. Oak wood is was taken from the general library, so it might not have an in-depth amount of material property information. That's just one thing to keep in mind when you're selecting materials, and sort of like keep in mind like what kind of results you might be expecting based on the materials you selected. So once you have your materials in, the next step would be to create your mesh. So a mesh, what this does is, so the method in which simulations are performed is through something called finite element analysis. And the method is such that your object is divided into multiple shapes. So right here, it's divided into multiple shapes like so. And calculations are performed on each shape at the nodes. The stress and whatever you're trying to calculate, the deformation, the stress, the strain will be calculated on each node and then summed up at the very end of it. That's kind of like the basic gist of how FEA analysis works. So by intuition, you can sort of tell that if you have a lot more of these tiny shapes, meaning a finer mesh, then you will be getting more accurate results because you'll be having more nodes across a greater surface area of your geometry, and therefore you'll be getting a bit more accurate results. The trade-off to that, however, is computational power. So the more refined your mesh is, the longer it will take for ANSYS to solve it, if it can even solve it. Sometimes ANSYS might be like, nope, it's too much, I'm not doing that, not today. So you have to be careful of what mesh you choose, and sometimes it's good practice to create your mesh, generate your mesh first, and then perform your solutions afterwards. So you have a question. If geometry shows up as two bodies, then what do you do to make it import as one? So in terms of adjusting your geometry to make sure it's inputted as one, that would mean you'd have to go back to space claim and just see what's wrong over there. Common problems might just be that the body is just split into two objects, or there is one option. There is well, no, that's really it. That's from what I can recall. It's just that the things that you need to suppress are suppressed, and your actual body for simulations are, you know, it's one solid body and it's not split into two. Yeah, no problem. So in order to create your mesh, like I've done here, the first thing you want to do is want to right-click mesh, click insert, and click sizing. And what this does is this allows you to choose what element size, or like the size of your elements on your geometry. In this case, I've gone with, I believe that's 3 millimeters. Yeah, that's 3 millimeters. So because this is a fairly small part of my door, I opted for 3 millimeters, and it is just the amount that it's the optimum amount that I need to get the result that I want. Any finer wouldn't really make it much difference. Any coarser, I might be getting, you know, slightly differing results. Let's see. What you can also do So in order to apply your body sizing, it will first ask you to select your geometry. And what you'd have to do is first you go to this top section right here and make sure your mouse is selected to body selection. And then you just click on your body and then it will be selected right here. It would say geometry 1 body, 2 body, or whatever your body's called. It will just be that. And then you can go ahead and type in your element size like so. Now, the next thing that you should add in your mesh is when you right click and click insert, you should add a method. So what a method is essentially the shape that will be, I guess, created on your geometry. So as you can see, because this is just a simple rectangular prism, I opted for, a square element shape. But with the method, you can choose different sort of shapes. You can go for tetrahedrons, hex, or a bunch of other things that, might lead to more accurate results, depending on, of course, the geometry of your model. So once you have these two things inserted and, once you've selected your body and inputted the desired parameters, what you would do next is you would just right click and either press update or generate mesh. And then ANSYS might take a second and then it will, here, I can just show you here. Oh, it's already, actually doesn't even do anything because it's already set up. But you would just right click and generate mesh and it will create the mesh like so. Some errors that you might get when generating a mesh would be A, your mesh is too fine, please make it bigger. Or B, the mesh cannot be applied to your geometry because your geometry is too complex. So this is a common issue that can come about in design projects. Say if you're designing, pretty complex materials with very tight corners or very small edges and whatnot. ANSYS might not be able to make a mesh around those geometries because of those very, very fine sections. So there are two things you can do to that. A, it is to either adjust the size of your mesh so that your mesh can actually fit inside your geometry. Or B, you would have to simplify your geometry even more or adjust it such that there aren't any problematic sections of your geometry that can interfere with your simulation. So just recalling an example, last year we had our glider competition, and part of the requirement was that students would have to perform a simulation on their design glider to make sure so that they can validate the results, because we couldn't do it in person, so we had to validate through online means. Some teams couldn't create a mesh on their glider for some reason, and one of the common reasons was that some people would just leave a floating line somewhere or a floating surface somewhere, and that would completely ruin the geometry, and it would be so tiny that they wouldn't even notice. So that's why it's important to check your geometry, make sure it is suitable for simulations before you actually get to the step, or you might be going back and forth over and over. So once you have your mesh created, it's now time to apply your boundary and loading conditions. So in the case of our sweet spot right here, how I will be applying my boundary conditions is first I'll be right-clicking static structural, clicking insert, and as you can see, I have a huge list of things that I can apply as boundary loading conditions. But the first thing I want to apply is a fixed support. So I'll just click that, and it'll be down here. I would click and select my geometry, and instead of body select, I'll be making sure I would be pressing face select and going around. Can I orbit? I can. Going around my object so that my 4 sides are fixed, because as you know, the sweet spot is connected to the remainder portion of the door, which is why this part is just completely fixed. So that's right. That's how you would apply a fixed support like so. To apply, I guess, my loading condition, my pressure, all I would have to do is just right click, press insert once again, and as you can see, my supports are down here, but I can also apply my pressure. Just click on pressure like so, and it would appear right here. This time, same thing. I would make sure to have face select in the top. Make sure I have this face selected. Make sure my ANSYS recognizes that I've selected one face, and then apply a pressure like so. In this case, I've applied a pressure of 10 megapascals. Yes, that's how much I applied. To the door. This is arbitrary. It's kind of just like applying a static force, an arbitrary static pressure or static force to your door. Just for the purpose of showcasing how the simulation would work out. Now, once you've applied your boundary loading conditions, you shouldn't be getting errors in this section. So that should be fine for you. Once you have your boundary and loading conditions set up, the next step is requesting ANSYS what things you want to observe from your simulation. So ANSYS isn't just going to go ahead and calculate every single thing. You have to request ANSYS, I want the total deformation. I want the strain that occurs. I want the stress that occurs. So to do that, you would go into the solution section, which is underneath static structural, right click, press insert, and you can see all of the solution things that that you want to see will be right here. If you're working with, say, a thermal simulation, you would also see thermal results like thermal heat flux, or I believe like vectors. You can see like the vectors and whatnot. So depending on the simulation you're performing, you'll be seeing different solution results. Same thing for your boundary loading conditions. So in this example, I have deformation, total deformation, equivalent elastic strain, and equivalent elastic stress selected, like so. Now, once I have everything set up and ready to go, all you have to do is just either right click here, go to the top right here and just click solve. And ANSYS will go ahead and take some time to solve your model. Because everything's already been solved, it's not doing anything, but for you, it will give it maybe 10 seconds or 5 seconds, and it will solve the model for you. And then once you're done, you can just go ahead and click on each of your results to see what you got. So here you have your total deformation, and as you can see, the middle part is the most deformed because the outer edges are fixed. If I want to see how it simulates, you can see as I apply the static structure, the static pressure, you can see it deformed like so. And you can do the same thing for equivalent stress and equivalent strain. It's important at this point to ask yourself if these results make sense. So for example, I had my sides fixed at these 4 faces. So it would make sense that I would be seeing some peak stress right here, because that's probably where my door piece will be breaking off of, right? One thing you would also want to make sure is the max stress that is occurring over here is less than or greater than the yield strength or the failure strength of the material, just so that you're actually with the pressure that you're applying, you're actually achieving the stress that you're getting. So I don't quite recall what the maximum stress of the wood was, but I think this is in e to the 8 pascals. I think that's 23 megapascals. I'm not exactly sure, but you would just compare with your yield strength and your engineering data, and proceed from there to make sure, like, okay, as you can see, my corners have reached past my yield strength of my door, and therefore this piece will break off. So that's how you would get results from a static structural simulation. And I'll be going more into like the questioning of your results in the example later in this workshop. So I'll be going through the remaining 2 modules a bit quicker because the bases are quite the same. I'll be going into explicit dynamics next. So it'll be the same thing. all you have to do is set up your engineering data, your materials. As you can see here, I've linked the materials that I have over here to the engineering data of my explicit dynamics. But I don't have the same geometry. Let me just show you what geometry I have. So I think the first example, right? It was me applying a sort of static pressure to the door, right, to get it to open. But as we all know, a static pressure doesn't really work. And trying to break down a door, you need a foot, right? That's how you break down doors in the movies, right? You break it down with your foot. And so in this explicit dynamic simulation, I will be simulating, I guess, the stress and deformation that occurs when I guess, eject this foot towards this door at a specific velocity, causing a specific amount of pressure on the door and seeing what kind of stresses occur from there. So as you can see here, I have two different geometries right here. Both of them will show up in ANSYS Mechanical. So in order to set yourself up for explicit dynamic simulations, you have to make sure your moving object and your stationary object are as close together as possible, because ANSYS will be simulating every single time that your two objects will be apart. So as you can see here, I think this is like 0.5 millimeters apart from each other. So the closer it is, the faster ANSYS will be able to solve your simulation for you. The whole basis around explicit dynamics is split-second simulations, seeing the results that from actions that occur within a split second. In the slides, for example, I showed you a picture of the car being run up against a barrier. You would use explicit dynamics for that, because you don't really care about the car going 50 miles an hour for 50 feet. You only care about the car just before it hits the barrier and right after it hits the barrier and the stresses that occur from there. So this example is kind of showcasing that. As you can see here, I have the door suppressed once again, and I only have the sweet spot and the boot, which is an imported part, which is why it has a different symbol over here. Once you have your materials set up and put them fairly close together, you can just click off ANSYS and you can go into explicit dynamics. You can go into ANSYS Mechanical. This again might take a while. All right. So this is your model in ANSYS Mechanical, and as you can see, both objects have made it into Mechanical. To just double check, once again, you go to geometry, and as you can see, you have two separate objects, like so, which we can assign different materials to. So for example, the sweet spot, I've assigned wood to, and for the solid, I'm assuming we're kicking the door down with the steel toe boots, because I don't want to injure my toe. So it's a steel toe boot with structural steel applied to it. Once you have your materials applied, you can go and generate your mesh like so. This will require two body sizings, one for each object. So as you can see here, I have a different mesh applied for each object like so, and I'll explain why for each. So body sizing 1 is for our sweet spot right here. And as you can see, I've chosen 1.4 millimeters as my element size. And that is because I'm specifically interested in the results of my door. Whereas my body size 2, it's comparatively a lot bigger, right? That is because I don't really care about any stresses or deformations that occur on the boot. So I don't care the accuracy of those results. This is a method that you can use to help you save computational time if you're working with explicit dynamics. If there is one object that you care a lot more for, then you can apply a much more finer mesh for that. As you can see here, I think this was done through an automatic method. So what I did here is I inserted automatic, selected both bodies, and just let ANSYS choose what mesh would work best for both of them. And this is what it came out with. The typical squares for the square object and a sort of like triangular shape, triangular elemental shape for the boot. As you can see, the boot elements are a lot bigger than the, see if I can better angle. Yeah, like the boot elements are like slightly bigger than the door elements. Okay. Once you have your meshings made, next it will be applying your initial and boundary your loading and boundary conditions to your object. So the first thing that you want to do is you want to set up your initial conditions. In this case, if you want to say apply a pre-stress to your object, you can do so. In this case, I haven't. But what I have done is I've applied a velocity to my boot at 50 meters per second, going in the negative z-axis. So all you have to do is the same sort of methodology. You would just click on velocity, body, select your shoe. And then in the details of velocity, you would scroll down and make sure you have minus 50 meters per second selected in the correct coordinate system. The next thing that you want to try and do is you want to go into analysis settings so that you can sort of just adjust the things that, just adjust how long or how many results ANSYS will be working with. So if you just scroll down to details and then end time, as you can see here, I've set the end time to like 6e to the minus 5 seconds. So it's a very, very, very small time range. That's because that's really the only time range that I care about. I don't care the seconds afterwards where the boot is like not in contact with the door. So this time range works for me, but for your project, you will want to make sure you have an accurate time range so that it can capture your entire simulation. But also don't go too big because then it will just mean more computational time. And if you scroll all the way to the bottom, I believe, and you go to output controls, you'll see something called result number of points. And so this is sort of like the frames that ANSYS will capture in your final like result. Like how you saw last time, how I played like the little animation. This is how many like sort of frames that ANSYS will showcase. So if you want more results per time, you can increase this, or if you want to save computational time and you only care about specific points, you can adjust it accordingly. So that's it. So that's how you would set up your initial conditions and your analysis settings. The rest is pretty straightforward. It would just be applying your fixed supports onto the faces of the door like before. But for the shoe, instead of pressure or anything, you'd be making the shoe, you would be applying a displacement to the shoe. So how I've done it here is I've only selected the face of the shoe right here. Because these faces are attached to the entire body, by moving these faces, I'll be moving the entire shoe body. And what I've done here is I've I've set my X and Y components. So my X and Y components to 0, meaning that my shoe can only go in the Z component. As you can see here, I've listed it as free. So that means you can go anywhere in the Z axis. But because I have my initial condition on my shoe to go this way, 15 meters per second to the minus Z, it will only go in the Z direction. It won't like hit the door and like, go up or down, left, right. It will only go in the Z direction. So once you have your fixed supports and your displacements ready, you can go ahead and start requesting answers for the things that you want to see. In my example, it's the same thing: total deformation, elastic strain, elastic stress. And you can just go ahead and click solve once you have everything ready. Explicit dynamics takes quite a while to do. So it might take like maybe a minute to do. So I've already have these already solved. All you got to do is just click and you can see your results like so. You can press play to see how it works. You can see the shoe is moving. Let me see if I can orbit. The shoe is moving and it is in contact with the door. Now, there's a couple questions that you might be thinking of right now, just based off this deformation that you see over here. The first thing is, why is your wooden door bending? Sorry, 1 second. So why is my wooden door bending and not breaking? The reason for that is because I chose wood oak as a general material that did not have any plasticity properties. So if I wanted to see any plasticity from my wooden door, like as in simulations, then I would be sure I would either add material property manually, or I would select a material in the engineering database that would have plastic properties. By plastic properties, I mean stress and strain tabulated data that goes beyond the yield strength of the material. So yeah. So in this case, there is no plasticity data in this wooden material. That's why you can see it's bending a bit due to its elasticity. And there was also no elastic data on the structural steel, which is why you can see the shoes also bending. I mean, it wouldn't be showing any plasticity anyways, because it's a steel toe boot, but these results, as you can see, aren't completely accurate. However, what you can still get from this are, the maximum stresses that occur on the door and on the shoe. Maximum stresses that appear like so. I can zoom out a bit. You can see the maximum stresses that appear on the door as the foot hits the door. You can see it's spreading. You can see like the stresses are spreading out quite a bit within the time frame that I've selected. So those are kind of the basics of explicit dynamics. Those are the general steps of how you can go ahead and perform it. Next, we'll be going into steady state thermal. Let me just close this. And this time, let me double click U. And I'm going to double click U2 if possible. I guess I'll double click the example so that I won't have to wait. All right, this is open. Let's wait for this to open. All right. And then open up our example like so. All right. And then while that's opening, I'll go over steady state thermal. So steady state thermal is very useful for when you're looking for like heat transfer in, let's say, piping applications. So in this example here, we have a fin going through sort of like a bent pipe going through like a fin that is typically used as like a heat sink, so to say. To make this sort of geometry, if you recall from our last week's workshop, you would know that you would have to use the sweep feature to get this sort of shape in SpaceClaim. So it's the same sort of steps right here with geometry. You make sure you have two different solids. make sure you apply them different materials like so. For the pipe, I have it as copper alloy, and for the fin, I have it as an aluminum alloy, both general materials. Next, I'll be creating the mesh, different body sizings for each of them. Once again, the body sizing for the piping is a lot smaller than the body sizing for the, or I think this one's just default, but the body sizing is smaller than the body sizing of the fin because I care about the heat properties that occur in the pipe and not so much of what happens in the fin. Okay. Now, to set up a steady state thermal simulation, it's it's a mix of the same steps between explicit and static, but not really. You have initial temperature or initial condition that you want to set. In this case, I've set the initial temperature to just room temperature, 22 degrees C. And I believe this is room temperature like in the entire system as a whole. It's not really like a body selection. Analysis settings are sort of the same thing. I set the time to 1 second, and you can adjust your output controls however you see fit. I don't think you have one. Yeah, you don't have result number of output points in this simulation. So all you can really do is just mess around with the end time. That's all that's, I guess, really important. Next, you would add, so for this example, I decided to add a convection on the aluminum. That means they'll be taking heat away from the pipe, from the heated up pipe. And I'll be adding a heat flow on the in the inside portions of the pipe. So for the convection, it was applied using the phase selection. Just double check that. Yeah, I believe it was applied on 2 faces, the front and back faces. And the heat flow was applied on the inward faces. It says 3 faces are here because this is one face, there's another inward face over here, and then a third one right like so. So that's how I applied the heat flux. The convection I set to 2.5, which I believe is the ambient air convection, or just convection you'd apply for just ambient air. And here I have applied a heat flow of about 150 watts. All right, once you have your initial and boundary conditions set up, you can go ahead and do the same thing where you can request ANSYS the results that you want. In this case, there you would have thermal options. Here you have temperature, total heat flux, or I guess an error if you want to see any errors. There is also, I believe there are ways to see the vectors. I believe that's in the directional heat flux. But there are ways you can see like the vectors and which way the I guess the heat is moving in different parts of the system. So that's also another option that you can request. And then same thing, like always, you just press solve and you can see your results like so. In hindsight, it seems like I should have maybe gone with the finer mesh on the piping, but it seems to be somewhat fine. As you can see, the gradient over here isn't very good, but these are the results that I'm kind of getting. As you can see, this is the temperature as that occurs in 1 second. So as you can see, when the heat flux is applied, this section right here like receives a max, gets like heated to the max. And you can also see that there is some temperature increase at these sections right here. As you see total heat flux, you can see that because of the convection condition we applied, we can see most of the heat flux is being put into from the pipe to the fin. That means heat is being transferred towards the fin. So it's good to just see these results and see if it makes sense over time. As you can see, over time, the pipe also starts to increase in heat flux a bit too. So those are the general steps in how you can perform a sort of steady state thermal simulation on your product or on your design. For my last part, I've gone over an hour, but for my last part, I just wanted to go over a quick example of static structural to get you familiarized with how you analyze a simulation and how you derive results from it so that it can actually be useful for your project. Because you can get pretty gifs of the heat flux moving and distributing, but if the numbers don't make sense, if the peak stresses where you're getting at don't make sense, then you may as well throw it out. So here is a bracket example that we're going over. And I've applied a geometry, I've applied a structural steel. So the material is structural steel. I've applied a automatic, let me see, I've applied an automatic, fairly big mesh to it. And because it's static structural, I've applied fixed supports on these like little holes right here and a 10 megapascal pressure on this this middle section right here. If you want to go ahead and make this bracket for yourself, feel free to look into the ANSYS simulation 8 sheet where the questions for this bracket and the actual drawing for this bracket will be shown. So if you want to do this on your own time in practice, then you can go ahead and do that using our 8 sheet. So these are a sort of initial loading conditions that I've applied to my bracket. And I've requested total deformation, strain, and equivalent stress. And as you can see, I've gotten the following results like so. So, 1 second. So some important questions to ask when you have a sort of result like this is, does it make sense? And there are a couple ways you can go about it. The first thing is, do the stresses that you're getting make sense? Are you getting abnormally large stresses over here? Or are you getting a stress such that like your material is failing, right? 10 megapascals shouldn't like be breaking the material so much, right? So it's important to ask these sort of questions. As you can see, the material is bending a lot over here, but that is because ANSYS sort of exaggerates the sort of how much it deforms. And I believe if you go to, don't quite remember where it was, right here. If you go to result and display, you can click either true scale or auto scale. So if I click on true scale and then press the deformation part again, you can see it barely moves. So this is like more realistic, what you would see in the real world. Whereas where it was on right now, auto scale is more like exaggerated to show deformation like that. Okay. So a couple of things, so like, yeah, you got to make sure that your deformation isn't crazy high. You have to make sure that the critical points make sense. A critical point is the point in which there is max stress. In this case, we have stresses right here, which makes sense because these seem to be the weakest area of our bracket if you have a load applied here and a fixed support over here. You would take note of the max deformation that occurs in that and compare with the yield strength of your material to make sure that it matches up for if you're under or exceeding that yield strength. If you see a weak point like that, you might want to think of some design questions. What can I do to this design or this geometry to improve it? In this case, I would think of to like maybe add some ribs or like some, not ribs, but like some fins onto the sides over here to sort of increase the surface area and distribute the stress a bit more evenly, to decrease the stress in that specific section to help mitigate failure. So these are the sort of questions that you should be asking when you're analyzing your result. So with that being said, I believe that is it for all I wanted to present in this workshop. Let me see. So that is about it. That is all I wanted to present in this workshop. If you, I hope you all learned something new from this workshop, gotten a bit familiarized with the ANSYS Workbench software, and can go ahead and perform your own simulation on your own time. If you have any questions, I'll be here for a few minutes to take on any questions. But if not, feel free to be sure to look out for our future UTDL events throughout this next few weeks and next semester. And with that, if there are no questions, I hope you all have a great evening. Thank you.